So question number 4. It's W20QP42. So now question number 4 is about electrochemistry. So starting with the first thing, he's saying what happens when you are electrolyzing KCl aqueous. So when you're doing that, your solution has, remember, it's got, and he's saying identify the substances that are liberated. So that's your cathode and anode. So that's the negative part, that's the positive part. There's going to be K plus 1, there's going to be Cl minus 1, and there's going to be H2O. And this one is going to be H2O as well. So I'll just briefly give you a simple overview of, you can either use your knowledge of O-levels electrolysis.
Oh yeah.
Because that works perfectly as well in most cases. But I'll give you the electrochemistry version, where you use this thing, where you use the electrochemistry equations, the electrode potentials. So there are two ways of solving that. You can either rely on your O-levels electrolysis, but that, remember, is incomplete knowledge. It's not. It wouldn't work always. But you can refer to this table, which is more correct. But in this case, they're not. It's just a 1 mark question, so you can kind of refer to your O-levels knowledge. What was your O-levels knowledge? That what's going to be released at? I mean, what was your O-levels knowledge? Your O-levels knowledge was, I'm going to do both, because it's just a simple 1 mark question. So I'll just do the O-level stuff. The O-level stuff was that the cathode had H plus 1 and K plus 1, and there was OH ions and Cl ions. Over here, since H plus 1 is lower down in the reactorices, so H plus 1 ions get liberated and H2 gas is produced at cathode. Yeah, that was your O-levels knowledge. And on the other side, you have OH minus 1 and Cl minus 1, but if the solution is concentrated or saturated, it's always Cl minus 1 that gets liberated. So it's going to be 2 Cl minus 1. It would lose electrons to form Cl2 plus 2 electrons, and chlorine gas is going to be formed. But what I'm going to do is I'm going to do the same thing. Remember, it's a 1 mark question, so I'm not going to go into, like, when I'm solving the question, I'm not going to go into a lot of detail with this. It's only 1 mark. But I'll just tell you how it's going to be solved. If it was a bigger question, if they had asked you for equations, everything. So the way you're going to solve this in A-levels is using electrode potentials. What will happen is, so let's get rid of the O-level stuff, which is going to be fine in this case, but the A-level stuff is, the way you're going to solve this is, KCl has 2 ions, K plus 1 and Cl minus 1. And water doesn't really ionize. It doesn't really ionize a lot. So the other molecule that's present is H2O. What will happen is, at cathode, the battery is sending electrons. So somebody over here has to gain electrons, right? That's what's going to happen. The battery is constantly, the cathode, the battery is sending electrons. So it's either, the electrons are either going to go to K plus 1 or they're going to go to H2O. So somebody is going to gain electrons. And who has a higher tendency to gain electrons? The one that has a higher E naught. I mean, the whole A-levels electrochemistry is all about this. The one who has a higher E naught has a greater tendency to gain electrons. So you got K plus 1, you got H2O. You're going to look at the data booklet, find where K plus 1 is, find where it's gaining electrons. So if I look at K is over here. I'll do some working over here. So if you look at K plus 1, gaining electrons, right? So the potential is minus 2.92. The other substance that you have at cathode is, let me change. So the other substance that you have at cathode is water. So it's either going to be K plus 1 gaining electrons, or it's going to be water that would be gaining electrons. So find equations for water gaining electrons. Water gaining electrons, that's this one. 2 water molecules, they're gaining electrons to form H2 and OH ions, and that's minus 2.83. So what did we learn in electrochemistry? What we learned in electrochemistry is, who gains electrons? The one that has a higher E naught. So out of the two, which one has a high E naught? It's going to be this one. It's going to be the It's going to be the water equation. So it's going to be, so the actual equation, they didn't ask for the actual equation. The actual equation is going to be 2H2O gaining 2 electrons, and they're going to form H2, and it will produce 2 OH ions, and the potential for that is minus 0.83 volts. So hydrogen gas is going to be liberated, but you're going to use the A-level method is this one. And the same thing would apply to the anode. At anode, they're going to lose electrons. So at anode, they're going to lose electrons. So you've got two substances at the positive anode. It's either going to be Cl minus 1, and since it's an aqueous solution, it will have water as well. So it's either Cl minus 1 losing electrons or water losing electrons. So who loses electrons? The one that has who has the greater tendency to lose electrons? The one that has the lower E naught. So you're going to look for Cl minus 1, you're going to look for H2, and you're going to look for them losing electrons. So Cl minus 1, that would be in the reverse direction. You got Cl minus 1 over here, losing electrons, right? So that is 1.36 volts, and you've got water, two equations for water losing electrons. So you got this one, not the 0.83. We want water to be losing electrons, so we have to think of it in the backward direction. Remember, in the electrochemistry table, in the forward direction, they gain electrons. In the backward direction, they lose electrons. So over here, at anode, we just have to think about them losing electrons. And we're going to go for the lower E naught one. Now, the lower E naught one, it's 1.23 volts, 1.77 volts, and there was one more equation, which is 1.36 volts. Now, the lowest one happens to be this one. This one is the lowest one. It has the lowest E naught, which means it has the greatest tendency to lose electrons, right? So you're going to select this equation. But the difference between these potentials, 1.23 and 1.36, is not a lot. And since they're using a concentrated solution, if you use concentrated Cl ions, where would the equilibrium shift? The equilibrium is going to shift backwards. Like if I do the working over here. So remember, changing the concentration changes the potential. So if I have a higher concentration of Cl ions in the solution, the equilibrium would shift in the backward direction. And whenever an electrode position, equilibrium position shifts to the left, what happens is that the E naught decreases. So instead of being 1.36 volts, it's going to be lower. So I'm going to give it a hypothetical value. Let's say it becomes 1.10 volts. So remember always, these potentials, all of the potentials that are calculated, they are calculated under standard conditions. So if the equilibrium shifts forward, the potential would be higher. If the equilibrium shifts backwards, the potential is going to be, it's going to be lower. So if you have a higher concentration of Cl ions, the equilibrium would shift backwards. It's going to produce a lot of electrons, and your electrode, whatever the electrode is, it would become more negative because there's going to be a lot of electrons being produced. So the potential would drop. It would become more negative. So instead of being a higher potential, it's going to be a slightly lower potential. It's going to be 1.10 volts. So anyways, they're using a concentrated Cl ion solution. If they're using a concentrated Cl ion solution, instead of this being 1.36, it might be a lower value. So who loses electrons? You've got two options, Cl minus 1 or these two equations. So 1.77, 1.23. In concentrated solutions, Cl is going to have a lower value. And it's going to be Cl minus 1 that would lose electrons. So Cl minus 1 would be the one that would be losing electrons to produce Cl2, and it will give off 2 electrons. So they're going to ask you all about this stuff. So I'll just give you a brief overview of how to do. I mean, it's a 1-mark question, so you'll be better off in this question using the O-levels concept of electrolysis. But the A-level concept was you got two things over here. Remember, there is no H+1, there is no OH ion in aqueous state. In O-levels, you studied that there was H+1 in OH ions. Water doesn't really ionize a lot. So think of water as water. Cathode, they're going to gain electrons, K+1 H2O. So what you'll do is find the equations in the forward direction, K+1 and H2O gaining electrons. Who gains electrons? The one that has the higher potential. So that is the one that gains electrons. So it's water gaining electrons to form H2. So over here, it's water that's gaining electrons. Who loses electrons at anode? Batteries trying to pull electrons away from it. So you've got Cl-1, you've got H2O. So who loses electrons? Think of the equation, find equations where they're losing electrons. So Cl-1 losing electrons. And you've got two equations for water losing electrons. Who loses electrons? The one that has the lowest E0. But the saturated condition changes the values. The concentrated solution of Cl-1 decreases the potential for this. Hence, it becomes the lowest. Okay? Is this clear to everyone? You clear, Simon, Baza?
Sir, which equation for water did we use for cathode?
For this one? Gaining electrons? Yes. We're looking for the equations where they gain electrons. So it's this one. Water gaining 2 electrons to form. So if you're looking for gaining electrons, right? Especially at cathode, you're going to look for it in the forward direction. And if you're looking for the substance losing electrons, you're going to look for the equation in the backward direction. Is that clear?
Yes, sir.
And the next one is it's about Faraday constant. So dilute sulfuric acid is electrolyzed, oxygen is liberated at the anode. So in this case, again, it's going to be water that would be losing electrons. So sulfuric acid will have. So I'm going to do. I mean, we can write the equation quickly. Sulfuric acid has, like, if you cathode and anode, and you've got H+1 ions. Now, sulfuric acid will have H+1 ions, and it will have SO4-2 ions, and it's going to have no OH, and it's going to have water on both sides. So he's just talking about the positive anode. He's just talking about this side. So who loses electrons? The battery is trying to pull electrons. So is it SO4-2 or is it water? So you'll just go over there, find equations where SO4-2 is losing electrons. Do we have one? I think we had one.
Yeah.
I mean, is there an equation where SO4-2? This one.
The one below water there.
Yeah, SO4-2 losing electrons and water losing electrons. So which one has the lowest E0? It's this one. It's 1.23 volts. So this is the equation where oxygen is getting liberated. It's 2 water molecules losing 4 electrons to form 4H+1 and O2. So remember, you had these two things: water or SO4-2 losing electrons, and who loses electrons? The one that has the lowest E0. So it's going to be water. So the equation that we are dealing with is this one: 2 water molecules losing 4 electrons. And what was the equation? We're dealing with this equation: 4H+1 and O2, right?
Yeah.
So we're dealing with this equation plus O2. Anyways, he then says that the electrolysis happens for 15 minutes with a current of 0.75 amperes. So you can use you can figure out the charge using Q is equal to I into T. Does anyone have a calculator? It's what do you get for this? It's current is
675.
0.750 into 15 minutes, right? So every minute has 60 seconds. So how many coulombs?
675.
6?
75.
So we're getting 675 coulombs.
Yeah,
What
that's
do we?
true.
So now, what do we do with that? What we do with that is we bring in the Faraday constant. The Faraday constant was that if you have 1 mole of electrons, right, it will have a charge of how many? 96,500 coulombs. That's Faraday constant. So if you have 675 coulombs of charge flowing through the circuit, so how many moles of electrons are passing through that? It's going to be X. So it's going to be 675 divided by.
96,500.
So the moles of electrons are 675 divided by 96,500. What do you get?
7.0 times 10 to
6.9.
the power.
6 point?
7.0 times
997.
10 to the power minus 3.
Why are we getting 6.94 or 7.0?
7.0.
6.99. Yeah, so that rounds off to 7.
Okay, so it's 10 bar minus what?
Minus 3.
Minus 3. So so we figured out that this is the moles of electrons that are flowing through the circuit. So it's 4:1. You can figure out the moles of oxygen now. So divide this by 4, you can find the moles of oxygen. So how much is that?
1.75 into 10 to the power minus 3.
So it's 1.75 into 10 to the power minus 3 and TK. And the next thing is you have to, that's the moles. And remember room conditions, so you have to find the volume of oxygen. So into 24 dm cube.
What did they give us?
So how much volume do you get?
0.042.
But that's in dm cube, right?
Yeah.
So convert that into, multiply that by 1,000 and you'll find it in cm cube, right?
42, yeah.
Okay, so just remember charge, you can calculate the charge through a circuit and you can convert the charge into moles of electrons. Now the next one is, and once you figure out the moles of electrons, you can figure out the moles of oxygen as well. The next one is the halogen, chlorine, bromine, and iodine differ in their strengths as oxidizing agents. These strengths are indicated by the E0 values for these halogens. So oxidizing agents, what does an oxidizing agent do? Does it lose electrons or gain electrons? An oxidizing agent, what does it do?
Loses.
An oxidizing agent gets reduced itself. I mean anything
yeah, exactly. Yeah.
So it gains electrons. So when we talk about things as acting as oxidizing agents, anything that undergoes reduction, that is an oxidizing agent. So anyone who likes to gain electrons, that's a good oxidizing agent. So E0 value. So who likes to gain electrons? The one that has a higher E0, right?
Yeah.
They like to gain electrons. So chlorine, bromine, iodine. So you're going to quote the values from the data booklet. And once you do that, 1 second, let me get rid of all of this as well. So where is chlorine, bromine, and iodine? So I've got iodine over here. That's 0.54 volts. I've got chlorine over here. Where's chlorine? Chlorine is over here. That's 1.36 volts, and I've got bromine somewhere. That's right at the top. So bromine is 1.07 volts. So if I just quote these values over here, what will happen is that the Cl2, Cl minus 1 electrode, that's 1.36 volts. The Br2, Br minus 1 electrode, that's 1.07 volts. And I've got the third one, which is iodine, and I minus 1 electrode, that's 0.54 volts. So who really likes to gain electrons out of the three?
Chlorine.
So that means that's a good oxidizing agent. And this one has a lower E naught value. It doesn't like to gain electrons, relatively speaking. So that's a bad oxidizing agent. So this is all you have to mention, because you have to quote the E naught values. You're going to state that the E naught values decrease down the group. So the strength as oxidizing agents decreases. That's it. And then they're saying, reduce which of the following, chlorine, bromine, iodine, will react with a solution of SN2 plus under standard conditions. So we're looking for, let me write down all the equations. So we're basically looking for them gaining electrons, right?
Mhm.
To Br -1, that would also, we wanted to gain electrons. And remember, who gains electrons? The one that has the higher potential.
Mhm.
So this is 1.36 volts. This one is 1.07 volts. This one is 0.54 volts. So this is going to gain electrons. So we want them to gain electrons. I mean, that's the only option, because Cl2 doesn't form positive ions. So when you're reacting something with Cl2, that's the only option you've got. Cl2 would gain electrons. So the other substance would lose electrons, right? Sn2 plus would lose electrons. And who loses electrons? The one that has the
Lowest.
lower E naught. So I'm going to write down the equation for Sn2 plus losing electrons, which is where probably on the next page. So loss of electrons happens in the backward direction. So it's probably this one, Sn2 plus, and that's 0.15 volts, right? So
Mhm.
we're gonna write that equation. It's going to be Sn2 plus Sn4 plus 2 electrons, and I want this equation to go in the backward direction. That's 0.15 volts. So can you tell me, will all three work with this? I mean, this is,
Yeah.
Yeah.
it will, because if you reacted with Cl2 has a higher potential, it's going to gain electrons, and this is the lower potential, it would lose electrons. If you reacted with bromine, that's the higher potential, this is the lower potential, so this would lose electrons, that would gain electrons, and the same with iodine. With which would the reaction be the fastest?
Chlorine.
Chlorine, because the E naught cell, the potential difference is a lot higher. So Sn2 plus would be able to lose electrons with either of them, all of them. Okay, so it's just 3 mark questions. Let me just check how it's explained. This is question number 4, right? So all of them. So the second mark is all E naught values are greater than 0.15, or E naught cell is greater than 0. And there's a third mark for the equation as well. So then, did they ask for the equation?
Mhm.
Include a relevant equation in your explanation. So you have to write an equation as well, like an actual equation. So that was the third mark. An excess of chlorine is added to a solution of Mn2 plus under standard conditions. Give the formula of the product of this reaction. So now I've got Cl2. I have only one reaction of Cl2, which is this one. And that's E naught is 1.36 volts. So Mn2 plus, I don't know what's going to happen to Mn2 plus. So I'm going to look for equations for Mn2 plus. There's one, Mn2 plus with Mn3 plus. There are two of them actually. Now, remember this, that Cl2, I mean, we've got Cl2. Cl2 can only gain electrons, right? I mean, that's the only equation, that Cl2 can only form negative ions. So if it wants to gain electrons, and this is 1.36 volts, sorry. So if this is 1.36 volts, if it wants to gain electrons, it should be the higher potential, right?
Mhm.
So Mn2 plus, on the other hand, would be the one that would be losing electrons. So what's the equation for Mn2 plus losing electrons? That's this one. Who loses electrons? The one that has the lower E naught, 1.49 volts. So it should form Mn3 plus by losing electrons. The E naught must be, I mean, over here it's 1.49 volts. So what do you think? Will a reaction happen or not? Cl2 with. Actually, there's another thing. There's another thing which is the using acidified Mn2 plus. So do we have acidified Mn2 plus anywhere? I don't think. No, I don't actually think. Is Cl2? Do we have acidified Cl2 somewhere? We don't. So, as a first thing, is this reaction possible? Because high E naught gains electrons and lower E naught loses electrons. The problem is this is not the high E naught and this is not the lower E naught. Is that clear? But they're saying that there is a reaction.
Yes, sir.
So acidified Mn2 plus aqueous. I don't think we have acidified. I don't think we have. If I rub all of this, just a second. Okay, let's try and figure this out ourselves first. Then we're going to look for the market scheme answer. Anyway, so we've got this equation Cl2, and that's 1, right? And Mn2 plus. Find all equations where Mn2 plus is involved. So there actually, that's 1. That's another one. Here's another one. Actually, I missed this one. There's one with water as well. So there's one with water as well. That's, I mean, water in aqueous state, water is by default present. So there are actually 3 equations. So we've got Cl2. Now Cl2 can only gain electrons. So it must be the high E naught, because that's the only reaction possible, that it would be gaining electrons, right? So these other ones would be the ones that would be losing electrons, and they must be the lower potential. So so the only possible reaction is this one, because that is the lower E naught. Like if I put the 2 equations together, maybe if you can see it over right now over here, Cl2 gaining electrons, that is the higher potential, that's 1.36 volts. Mn2 plus losing electrons, that's 1.23 volts, that's the lower E naught. So that works perfectly. Okay, is that clear?
Yes, sir.
These other equations, they don't work, because 1.49 volts is actually the higher E naught, so it's not going to work. The one who loses electrons is the one that's the lower E naught. This one is also not going to work, even though it's the lower E naught, but it will not be Mn2 plus that would be losing electrons, because they were talking about Mn2 plus, not Mn. So we can't use this equation. So you've got these 2 equations, and the product is going to be MnO2. That's what my product is going to be in this case. Okay. And in the paper, the way you're going to do this quickly is you're not going to write the equations over here. You're going to do all the working over here. You're going to solve the question like this, that Cl2 is reacting, so it's gaining electrons, must be the high E naught. So if it's reacting with Mn2 plus must be the lower potential, must be the one that would be losing electrons. So the only lower E naught is this one. So the product that would be formed would be MnO2. So you're going to be much quicker, TK, if you're just doing all the working over here. So MnO2 should be the answer, and that is the correct one. TK, is that clear?
Yes, sir.
Yes, sir.
Achha. Here there's the other one electrochemical cell can be made by connecting an Fe3 plus with this electrode. Calculate the standard cell potential. So Fe3 plus, Fe2 plus. So I mean, we'll just open the data booklet again. Okay, let's get rid of. So we're going to do all the working over here, because they're not looking for the working. They're just looking for the E naught cell. Where's the Fe3 plus Fe2 plus electrode? It's this one. It's 0.77 volts, right? And the other one they're talking about is the S2O8 SO4 2 minus electrode. So where's the S2O8? Let me get rid of this. So where's the S2O8 and SO4 minus 2? It's this one. It's 2.01 volts. So that is definitely the higher E naught. What does the higher E naught do? It gains electrons. The other one is the lower E naught, which is this one. It's 0.77. So that's your lower E naught. So what does the lower E naught do? It loses electrons. So your reaction is going to be, I'm going to write down, so they're not actually looking for the equation, they're looking for the E naught cell. So what is the E naught cell? E naught cell is, how do you find the E naught cell? It's the reduction potential minus the oxidation potential, or basically higher potential minus. So it's going to be 2.01 potential difference, 2.01
minus 0.7.
minus 0.77. So 2.01 minus 0.77, which is going to give you 1.47.
1.24.
Is it 1.47 or 1.43?
1.24.
1.24, sorry.
Mm.
So this comes out to be 1.24. State the material that should be used in the electrode in each cell. So if you have aqueous ions, what would the electrode be made up of?
Platinum. Mhm.
So it's going to be made out of platinum because the ions would be part of the solution.
Mhm.
And if they want to gain electrons, they're going to gain electrons from the platinum inert metallic electrode. If they want to lose electrons, they're going to lose electrons on the inert platinum metallic electrode. So the electrode would either become negative or it would either become positive, depending on what they like to do. If they like to lose electrons, it's going to become more negative. If they like to gain electrons, it's going to become more positive. And in both cases, it's going to be made out of platinum. Whenever you have aqueous ions, it's always going to be made out of platinum. And the next one is, describe one change to each half cell that would increase the value of the cell potential. So I've got, one of them was this one, reversible, and this is Fe2 plus. This is 0.77 volts. This one was S2A2 minus. And this was 2.01 volts, right? So if I want to increase the value of the cell potential, so I need to make this even lower, right? And I need to make this even higher. So we did discuss that you can change the potential, you can change the standard potentials by changing the condition. How do you make it lower? You can make it produce more electrons. You want to shift it in the backward direction. So you can either increase the concentration of Fe, you can increase the Fe2 plus concentration. Is that clear?
Yes, sir.
And if you want to make it higher, you should push the equilibrium to the forward direction. So how can you push it in the forward direction? You can increase the concentration of the S2O8 ions. Is that clear?
Mhm.
Or vice versa, you
So
can.
what if we wrote decrease Fe3 plus concentration?
I mean, you can do that as well. You can, but it's better to just focus on the reactants, because I think in this case that would be acceptable as well, because they're talking about the electrochemical cell. So in that case, that is possible. But if they weren't talking about the cell, they were talking about the same reaction. So when you're doing a reaction, you just have these ions, right? Basa, is the point clear?
Yeah.
Yes, sir.
Like if you didn't have electrodes, but you had you were just doing the reaction, so you'll just mix Fe2 plus with S2O8. Fe2 plus would gain electrons, so you lose electrons to form Fe3 plus, and S2O8 would gain electrons to form SO4 minus 2. So the concentration of Fe3 plus and SO4 minus 2 in that case would not be in your hand. You will not be able to change the concentration of the product.
Oh, okay.
But in this case, since they were talking about a cell, So both ions were already present. So you can change both. I mean, you can either increase this concentration or decrease the concentration of Fe3 plus. Okay, is that clear?
Actions with more negative.
Yes.
Okay.
So let's move to the next one, which is define the term transition element. So what's a transition element? It's a D block element. And what does it do? It forms stable ions with incomplete d substions. TK, I had sent you notes about inorganic, TK, including transition metals. Most of the questions are going to be exactly the same. For transition metals, it's always the same question. So form stable ions with incomplete d substions. Let me also. So it forms stable ions with incomplete or partially filled d subshell. So anyways, complete the electronic configuration of an isolated gaseous Fe3 plus. That's 26 electrons. So it's 1s2, 2s2, 2p6, 3s2, 3p6. Then you have 4s2, and 3d would be 6. But since this is 3 plus, so this would be gone 2 electrons, and there would be just 5 electrons left in the D. Name 2 transition elements whose isolated gaseous atoms have the same number of electrons in the 3D subshell as an isolated gaseous Fe3 plus ion. I mean, that is. I said name 2 transition elements whose in the 3D subshell. Oh, that's easy. That's easy. Why? Because all you have to guess is who has 3D5. So actually 2 elements. Let me go over here. Look at the periodic table. Remember, calcium is 3D0 and 4s2. Like if you want to be quick with the electronic configuration, because questions related to electronic configuration can be very time consuming. But you should know what the hacks are. Scandium is going to be 3D1, 4s2. Like even if you write the whole electronic configuration, this is what's going to be. Titanium would be 3D2, 4s2. Like if you're going across transition metals, you're basically filling the 3D subshell. Vanadium would be 3D3, 4s2. Chromium should be 3D4, 4s2. But remember, chromium is a special case. What happens is that instead of 3D4, it's actually 3D5.
Yeah.
So chromium is 1.
Mm-hmm.
And manganese, I mean, you can just continue with manganese, that's 3D5, 4s2, right? So there are actually 2 elements that have 3D5. Chromium should have been 3D4, 4s2, but instead it's actually 3D5, 4s2. So chromium and manganese will both have 5 electrons in the D subshell. Is that clear?
Yes, sir.
And then you have cobalt 2. Sulfate is added to water to form a pink. So I'll just quickly let me open the notes for this. TK transition metals. So there are 2 ligand exchanges for copper and cobalt that you have to memorize. So for example, that's your these are the notes that I sent in the group earlier. So you've got to memorize these color changes. That's 3D subshell, this one. For copper, remember the complex. Copper with water, that's blue. If you add NH3, copper becomes deep blue. If you add HCl, Cl ions surround it, and that becomes yellow. If you add OH ions, it becomes copper hydroxide, that's a blue precipitate. With cobalt, it's going to be the exact same complexes. Cobalt with water, cobalt with OH ions, cobalt with NH3, and cobalt with Cl. But the colors are different. So it's going to be pink with water. So you have to remember these 2. You have to memorize all of this. So if I go back to the question, he's saying complete a diagram to show he's saying cobalt sulfate is added to water. So complete the diagram. So, and sorry, it was added to water. And then an excess of hydrochloric acid was added to the solution to form a blue solution containing complex ion Q. So we're talking about Q over here. So you added to water, it became surrounded by water, but now it's surrounded by Cl ions because you added concentrated HCl. Cl ions are bigger in size, so there would be just 4 of them around it. So it's going to be tetrahedral. So Cl ions and the cobalt will have a charge of +2.
Yeah.
And there's going to be one more Cl -1. You don't write the individual charges, you write the overall charges. The overall charge is going to be -2 on the entire thing. I mean, it's going to be -2. CO is +2, Cl -1, -1, -1, -1. Name the type of reaction. That's a ligand exchange. Okay, is that clear?
Yes, sir.
Explain why the solutions that contain transition metals are often colored. So it's the same exact explanation. Why are transition metals colored? They're colored because when they get surrounded by ligands, the ligands, they create repulsion in the D subshell. So in some of the D subshells, the repulsion is higher because the ones that are facing the ligand, like if the water molecule approaches the molecule, it becomes harder to keep electrons in this 3D orbital. So I'll just give you a brief overview of all of this. That remember that where's the 3D subshell? So remember, there are 5 different types of D subshells. 3 of them, the electron density lies between the axes. 2 of them, the electron density lies exactly on the axis. So when complexes are formed, where's the color thing? Just a second. So this one. So when complexes are formed, the D subshell was degenerated. They had the same energy level. They were identical. But because of the presence of these lone pairs from ligands, the green ones, it's harder to keep electrons in the green ones. It's easier to keep electrons in the pink ones, the ones that are in the middle. So the D subshell splits into 2 sets of orbitals. The green ones, it's harder to keep electrons over there. Why? Because the lone pair is creating repulsion. So because of the lone pair, it's harder to keep electrons in this green one. The pink one is slightly further away, so it's easier to keep electrons in the pink one. So some of the orbitals are going to be, it would be easier to keep electrons. Some of the orbitals, it would be harder to keep electrons. Splitting of the D subshell happens only when the ligands approach it. Otherwise, they were all at the same energy level. And why are they colored? They're colored because electrons, the D subshell is partially filled. So electrons can jump from the lower energy D subshell to the higher energy D subshell after the splitting has happened, and they can absorb a particular frequency from the visible spectrum. This energy gap exactly matches electrons, frequencies that belong to the visible spectrum. So you start seeing a complementary color. So this is the explanation that you're going to write, that due to repulsion from lone pairs on ligands in metal complex, D subshell splits into 2 energy levels. Electrons from low energy D orbitals gain energy and moves to the high energy D orbital. The energy gap delta E matches frequencies which are part of the visible spectrum since E0 to HF, hence the complementary color is C. So if it absorbs red, you're not going to see red. And the Markin scheme answer would be the same. That the D orbital split, lower D, higher D, electron absorbs energy from the visible region, electron becomes promoted, moves to the higher D orbital, jumps to the higher D orbital, and a complementary color is C. So just remember, make sure you just, try to understand the notes as well, but just memorize all these answers because transition metal questions are going to be very typical. They're always going to be repeating the question. It's going to be the same type of question. So that's the 4-mark answer for this one. TK. Is that clear?
Yes, sir.
And the second part is, why are the colors different? What happens So that's the second part. Why does the change of ligands changes color? Because if you have a different ligand, it will exert a different amount of repulsion, which creates a different energy gap as the d subshell splits. Like if I change the ligand, the amount of repulsion that another ligand's lone pair would create would be different. So the energy gap that would be created would be different. If the energy gap is created, a different frequency would be absorbed. So instead of orange color being absorbed, it might absorb a blue color. So the answer to that is that the delta E is different. So a different frequency is going to be absorbed. So you always get these two typical questions on this. So we can, how much is left? So that's a big question. So we can try and do the other one. Name. You see, in this reaction, a solution of bidentate ligand is added to an aqueous solution of cobalt 2 sulfate. Oxide is then bubbled into the mixture, forming a complex ion in the formula. So what is happening is cobalt undergoes two types of reaction. One type of reaction is the same as is described. Name the other type. That is oxidation or redox. Because remember, initially cobalt was +2, but now over here cobalt is +3. How did I figure out it's +3? Because this molecule was neutral, so the charge is coming from cobalt, not from this molecule. And he's talking about the bidentate ligand, this one, which is this one, CH2. He's drawn the skeletal formula of this. So that is also, and again, this is going to be the same question, bidentate ligand. So let me I'll just show it over here. That's isomers. Haji.
In the ligand exchange, changing the ligand basically changes the color of the solution. What if instead of like keep the ligand same and we change the metal ion?
Same thing. No? Okay, that metal ion will have a different d subshell arrangement.
Yeah.
Okay. Just this one, bidentate ligands. This is so this one. He's basically talking about this one. Bidentate ligand is that the ligand is able to form two dative bonds. So they're using a skeletal formula, so I'll just quickly do that. But remember, it's going to be the same question. So just read the notes. Everything would be kind of the same. So it's going to be an octahedral complex. And you got this molecule, so there's going to be N. There's going to be another N. This lone pair and this lone pair. So two dative bonds. And then there's going to be another one, N, and they would be connected. And two lone pairs. And this one as well. Okay. So lone pairs. The other question is isomeric form. So remember, when you have bidentate ligands, there's going to be optical isomers, which is also given in the notes. It's going to be the same exact question every time. Whenever you have, where's that optical isomerism? Just a second. Probably right at the end. So this one, optical isomerism happens in bidentate ligands. So this is the same molecule. There's going to be a mirrored version. Just draw the mirrored version. That's it. So it's going to form optical isomers. So that's about it. So all you have to do is just draw the mirrored version of this, and then name the type of isomerism shown. That's optical. State the coordination number of cobalt in these two isomeric. Cobalt is making 6 dative bonds. So coordinate bonds is coordination number. That's 6 dative bonds are being formed. And then you have, you think the stability constants of 3 complexes of mercury are given. Write an expression for the K stability of HgCN4 2-. So the stability constant is that when you have an Hg aqueous ion, which is going to be 2 plus, I think, in this case, because Cn, remember, is -1. So there are 4 of them. So He must be 2. So what is the ligand exchange that's happening? There would be 4 CNines coming in. There's going to be an equilibrium reaction. This is going to be aqueous. And it would form HgCN4. And the overall charge would be -2. So that's basically the ligand exchange that's happening. An aqueous ion, you add CNines and it forms this. So stability constant is the Kc for this reaction. It's product concentration, which is going to be Hg CN4 concentration 2 minus divided by the reactants, which are Hg2 plus and Cn -1 concentration, and that's going to be power 4. So stability constant is you've got an ion, you're changing the ligands. So stability constant is the Kc for the ligand exchange reaction. And if this has a higher value, that means there's going to be more products. So that means ligand exchange would happen. That means there's going to be more of this. So an aqueous solution containing He2 plus is added to a solution containing equal concentrations of Cn -1, Cl -1, and I. The mixture is left to reach equilibrium. So when you add all of these ligands, by looking at the value, remember, higher value indicates there's going to be more products. So which one has the highest value? It's the first one, right?
Mm.
So that means this has the highest probability of getting formed. So predict which of the complexes is present in the resulting mixture in the highest concentration, which is present in the lowest concentration. So this has the highest K stability value. So this one is the highest one. And this one would be present in the lowest concentration because it has a lower value. So there's lesser chances of the products forming in this case. Is that also clear?
Yes, sir.
So just remember, K stability is its product concentration divided by reactant concentration. So if the K stability value is higher, that means more products are going to be formed. More ligand exchange would happen. So K stability is higher, so more of this would be formed. K stability is lower, that means less of this would be formed. So this would be more, and this would be less. So agar aapne mercury ke andar, if you had mercury and you added all of these, so this has the higher concentration, more of this would be formed, and the middle one, less of this would be formed. Okay, is that clear? So we're done with this. Just remember, for transition metals, my advice is just look at the notes. TK, it's pretty much. I mean, you have K stability written over here as well. That so inorganic is mostly just you just rewrite everything that's written in the notes. There's not a lot of they won't ask a lot of different questions. It's going to be the same typical questions that are going to be asked. Okay, so let's continue tomorrow then. Okay, everyone.
Sir,
Yes.
can you do me a favor, please? Do you mind if, because I didn't have these notes,
I'll send these notes
to the group?
Yeah, I'll send these notes.
Okay.
Haji.
We did like a chain reaction in electrochemistry. Can you briefly go over?
Chain reaction? Acha, chain reaction. Do you want to go over that?
Yeah, a little bit. Like I think I'm forgetting what it was.
I'll go through that in the next class then. Okay.
Thank you, sir.
Okay, take care.
Thank you so much. Okay.